So the last thing we're going to do this week, which is a fairly light week for the organic, but one filled with important concepts, so we're going to touch on cycloalkanes. As far as I can tell from looking through the A-level, these are things that are kind of taken for granted without any big discussion. But it is very worthwhile having a discussion on some aspects of cycloalkanes. Not a huge amount, but just a couple of fun little concepts we can discuss. Anyway, what is a cycloalkane? Well, it's an alkane that's got a ring of carbon-carbon bonds, hence the cyclo part. So cyclopropane is the smallest possible ring because you can't make a ring out of one or two carbons. So cyclopropane, as the name would imply, 3 carbons in a ring. 3 ways to depict it: either the skeletal structure, the compressed skeletal structure, or of course the molecular formula. No prizes for guessing the next one: cyclobutane, which looks like a square. 4 carbons, 8 hydrogens. Cyclopentane looks like a pentagon. Cyclohexane looks like a hexagon when you draw it like this. Not going to go too far, but we will do the heptane, which looks like a 50p coin, and the octane, which is just a nice, cool stop sign type of thing. So C3H6, C4HH, C5H10, C6H12, 7H14, and C8H16. Do you spot the homologous series? Well, they have similar type properties, of course, and their general formula is CnH2n, so twice as many hydrogens as carbons. Now, we are going to trace these general formulas for quite a bit throughout this course. Why is this CnH2n, whereas alkanes, of course, without the cycle, were CnH2n plus 2. We've lost 2 hydrogens. The reason for that is that we made a new carbon-carbon bond. And so each of those carbons involved in that new bond that we made had to lose a hydrogen to make room for the new bond. And if I just quickly show this with pentane, with some pretty colors, here's pentane, where we got red and a pink at the ends. Now imagine the pink and the red carbon forming a bond, so we're going to make cyclopentane just like that. Well, again, red one has to lose a hydrogen, pink one has to lose a hydrogen to give the CH2CH2, so that each carbon has 4 bonds. So whenever you make a new carbon-carbon bond like this, you remove 2 hydrogens. Now we can make that carbon-carbon bond by making a ring, as we just did, or of course next week, as we're going to see, making double bonds or triple bonds. And so you can get a little taster of what the general formula of alkenes will be like, but more on that next week. Now, I'm not going to dwell overly on the physical properties associated with cycloalkanes, but it is rather interesting to note that, as you might expect, some of those smaller ones are extremely unstable. If we look at the heat of formation for the triangle and the square, it's positive. In other words, these are unstable with respect to their elements, is the fancy way to put it. If we look at the heat of combustion, how much energy you get out per CH2, we see that we get a lot more energy out per CH2 for cyclopropane than we do for butane, and both of those much bigger than the normal one there. Now, what that means is that if when you burn them, because let's face it, you're just burning carbon-carbon bonds, carbon-hydrogen bonds, if you've got some extra energy there, it means that there was some extra energy stored up in these small molecules, a little bit of strain energy. Now we can see that by looking at the angles. If you think back to your VSEPR, all of these are carbons that have 4 bonds, so they should all be tetrahedral, so they should have angles of 109.5. Now, poor little carbons in cyclopropane, they've got to have an angle of 60, and there's absolutely nothing they can do about it. You can't distort a triangle in the slightest angles of 60. No wonder they are unstable with respect to their elements. That's a positive heat of formation, and no wonder we see that extra energy that you can get out when you burn them. Cyclobutane, a little bit better than cyclopropane, still positive heat of formation and still more heat coming out per CH2, so there must be some extra energy there, and you can kind of see it because in a square the angle's got to be 90. Well, it wants to be 109.5. So what cyclobutane actually does is it puckers ever so slightly, so it's not a flat square, it's a little puckered 3-dimensional 4-membered ring. Now we get to cyclopentane, hexane, and so on. You'd think cyclopentane, which if it was just a flat pentagon would have an angle of 108, you'd think that would be fine. Cyclopentane has this so-called envelope conformation, just designed again to relax a little bit of that strain and the constraints that putting the ring does. Cyclohexane, most famous of the cycloalkanes and the one that we will be focusing on for the rest of this movie, doesn't adopt a flat hexagon, it adopts predominantly this so-called chair conformation. You can see why there's a chair. There's the leg rest, there's where your bottom goes, and that's where your back goes. Now there's all kinds of fun things that one can do with the conformations of cyclohexane, and that will be an extension topic associated with this module, probably a few days away from putting that fully thing together, because the conformation cyclohexane rather fun. For now though, we're going to say when you see cyclohexane, it exists as a chair.